Hi, welcome to our first video for 5.3, Investigate Transformations of Sine and Cosine Functions. In this video, we're going to learn how to apply all the transformations that we've learned in previous chapters to a basic sine and cosine function. Okay, in order to investigate these transformations, we're going to use Desmos, and we're going to apply the transformations and see how they change the base graph. Before we begin, though, it's really important that we know the base graphs for sine x and cos x. So I'm just going to draw those out real quickly just for our reference. We can do that below here. So this graph here, y equals sine x, I basically just remember some main points for it. So in this function, x represents our angle along the x-axis. Okay, and I like to get one full cycle in. When I say one full cycle, I'm actually kind of referring to like the unit circle going all the way around. Okay, so remember the unit circle. Okay, this point on the unit circle, the ordered pair, the x value is cos x and the y value is sine x. Okay, and this goes, we can label the axes here. So let's just, because we're going to graph sine x, let's just focus on the y value of this ordered pair. So this angle here, we're going to call it x. So as x begins at 0, the y value of this point is going to be 0. And as we rotate, the y value is going to go up all the way to a maximum of 1. And if we keep rotating past 90, it goes back to 0. And if we keep rotating past 180, because this would be 180 all the way here, if we keep rotating past that, we now have negative values. And the lowest value is negative 1. And if we keep rotating past, this would be 270. If we keep rotating past, the y value on this ordered pair would eventually be 0. So we see that sine actually has a nice round trip. It starts at 0, goes all the way up to 1, back to 0, then down to negative 1, and then back to 0. And that's exactly how the function looks. Okay, so to graph this, I mark off 1. That's my maximum value. The minimum value is negative 1. One full cycle is 360 degrees, so I mark that off here. So my sine function, I'm going to draw this in pink. It starts at 0 because that's the y value here when we begin at 0 and we rotate this way. And once it goes all the way around 360, it ends back at 0 again. So that I kind of already got two nice points that I know that are going to work. To get the rest, what I do is I actually take this section of the x-axis here and I chop it up into 4 pieces. So I first cut it in half. Okay, if I cut 360 in half, I get 180. Okay, then I cut each one of these sections in half. So half of 180 is 90, and then I now cut the next part in half. Halfway between 180 and 360 is 270. Okay, I can now get my nice main points on here. So I'm gonna go back to pink. So when x is 90, that means when we rotate 90, my ordered pair up here, the y value, sine of 90, is going to be 1, a maximum value of 1. So I can draw a nice point up here. As I keep rotating to 180, the y value is going to be 0 at that point. So if I rotate 180, this ordered pair is negative 1 comma 0, so the y value is 0. So I know I'll have a point right there. Okay, and if I continue rotating all the way down to here, when the angle is 270, okay, this ordered pair is going to be 0 comma negative 1. So the y value is negative 1. So I'll have a point negative 1 right here. So I always remember these 5 points for sine graph. Quick way to remember it is think we're going to start at the origin and we go up and then we come back down and we do one full cycle. So we start at the origin, we finish at the origin. Okay, start, go up to positive 1, and then come back to all the way down to negative 1, and then go back to 0. So it's going to draw a nice curve through here. Okay, practice drawing nice curves. Don't draw straight lines through these because it is a sine function. Okay, and you can also go like that and show an arrow that it's going to continue. It also goes this way too. And I draw a nice arrow for that. Then we can just label the graph y equals sine x. So that's our base function. I'm gonna label the ordered pairs 0, 0, 91, 180, 0, 270, negative 1, and that one right there, 360, 0. Those are 5 nice points that I can always depend on when graphing sine x. Okay, let's quickly do cos x. So cos x, I'll draw this in green. Okay, we're now focusing on the x value of this ordered pair. So we're starting down here at 0. The x value is going to be 1. Okay, so we will draw that. So we have y, we have x. So my first point is going to be 0, 0, 1. So that'll be up here. Let's label the y-axis. Positive 1 and negative 1. Okay, so as this point rotates, once I rotate 90 degrees to here, this ordered pair is going to be 0, sorry, it's going to be 90, comma 1, because we're all the way up here. So I like to plot that point next. So 90 will be about here, kind of the same as above. Okay. If you want, we can label the rest, 180, 270, 360. So this point, sorry, let's redo this one again. When we rotate 90, if x, so my ordered pair right here is 0, comma 1. So that means cos of 90 is 0. Remember, it's always the x value. So we have a point right here. When we rotate 180, we would end up right here on this point. This says the ordered pair negative 1, 0. So the cos value is negative 1. So cos of 180 is negative 1. That's here. You can already see this is kind of going to be my curve going through here. Okay, at 270, that puts us all the way down here. The x value is 0 at this point. So we'd be back up to 0. And then if we rotate a full 360, this ordered pair is 1, 0. So cos is the x value. It's going to be 1. That's y equals cos x. Okay. Just to label those points real quickly, 0, 1, 90, 0, 180, negative 1, 270, 0, and that last one there is 360, 361. Those would be the 5 key points for that. If you can remember these graphs, it'll really help you out doing the transformations for these functions. Okay, let's begin the Desmos simulation. Okay, so there's a link. You can see I have in blue right here, sine x. That's my blue graph on the curve. Okay, notice it looks like what I drew before for sine x. It starts at the origin and then goes up. Okay, and at 360 it does one full cycle. You can see that. Underneath it, I have a red graph, and notice the way how this looks. It says y equals a times sine k x minus d plus c. What we've done is we've incorporated all the transformations that can be done to sine x. Let's just go back here for a second. So all sinusoidal functions are going to follow this form. When we have to include all the transformations, we're going to have a times sine k x minus d plus c. Okay, remember this looks a lot like our y equals a times f k x minus d plus c. Remember f represented some function. Well, now it represents a sine function. Okay, So this part here is like my new angle for sine. Remember we always do sine of an angle? Well, instead of just having x for our angle, we have two transformations, k and d. This is going to affect things horizontally. Okay. After we do sine of this angle, we then multiply by a and add c. That just affects the y values. Okay. The nice thing about these is a, k, d, and c, they do the same thing that they've done for all the other functions. Okay. We're just going to double check it through here as we go through the investigation. So the first part I'd like to investigate would be a. I actually would like to encourage you maybe to pause the video and you can go into Desmos, click on that link, and you can experiment with Desmos. Experiment with using different values for A. Okay, A is one of the sliders, and you can change the values. So I'll show you real quick. Not that one, it's up here. Here we go. So you can see the slider A right here. Okay. So what you can do is you can adjust the value and see how it changes the graph. Okay, so if you notice, it actually changes the amplitude of the sine function. Okay, remember amplitude is the distance. It's half the distance from max to min. So we're increasing that distance as we increase the y value or decrease it. Okay, so let's go to the investigation. So if you want, we can do this one together and then you can pause and do the rest on your own. So it says if A is greater than 1, the amplitude is greater than 1. Yes, we did see that. Let's just double check. If I make the A value greater than 1, the amplitude is also greater than 1. Okay. Next, we were asked, put A between 0 and 1. So A between 0 and 1. So that will be somewhere right around here. Okay, it actually decreases the amplitude. Okay, so if I make A about 0.5, it's about half the amplitude of what it normally was. Okay, let's also, maybe before we do this, we should probably move some of these sliders, reset them to their initial values. That way we're only doing one at a time. So I'm going to make K to 1. I have D to 0. I'm going to change C to 0. Here we go. Okay, so now we can actually really see the A value is about a half on the red graph to what it is for the blue one. Okay, so we can go ahead, we can write that in here. So we can just say amplitude is less than 1. Okay, so it gets smaller. Okay, what if we go between 0 and negative 1? Well, you could probably make this prediction. If I make the amplitude between 0 and negative 1, notice the graph flips. So it actually reflects, and the amplitude is still small, still smaller than the blue one. So we can write that in. Reflects along x-axis, and amplitude is less than 1. Okay, kind of fits in the box here. All right, so now we have A smaller than negative 1, so like negative 2. So let's move this a little bit further, and now it stays reflected, okay, because normally the graph looks this way. It starts at the origin and goes up, but now that it's negative, it starts at the origin and goes down. Okay, so the amplitude increases and it reflects along the x. So we'll keep some of the same stuff. Reflects along x-axis, and amplitude is greater than 1. Okay. All right, so if you want to pause the video now, maybe you might feel comfortable enough manipulating these and doing the rest of the investigation. I suggest you keep these at 1 and these at 0 whenever you're going to reset to start a new parameter, right? These are all the parameters. So to start k, I would put this back to 1, the a value, put it to 1, and then begin. Okay, so let's go take a look. What about k greater than 1? So let's reset this back to 1. So as I increase k, notice the red graph. It looks like it's being compressed like a spring. Okay, it's being horizontally compressed. Okay, so we can say that it's being horizontally compressed. Horizontally compressed. That also means the period is smaller. Okay, so let's go back real quick. Okay, so we started at 1, and then notice as I increase k, the cycle, the length for one cycle gets smaller because it's being compressed. Okay, what's our next value? So between 0 and 1, let's go take a look at that. So at 0.7, notice the red graph is getting longer. It's being horizontally stretched. Period is getting longer. So we can say horizontally stretched. The period is larger. Okay, larger than the base graph. Now let's do from 0 to -1. Okay, you notice what happens? It now looks like it flipped. Okay, and between 0 and -1, it's also the period's longer. So if you remember, when k is negative, it doesn't reflect along the x-axis, it actually reflects along the y. So it reflects along the y, and the period is larger. So it reflects along y-axis and horizontally stretched. Okay, we would actually say it's being stretched by a factor 1 over k. Remember, for the k value, it's always 1 over k. So we could actually say that up here for this one. We could say by 1 over k. So if k is a small number, this gets big. That's why it's horizontally stretched. Okay, if k is a large number, greater than 1 over k becomes small. That's a small number. That's why we use horizontally compressed. Okay, last one. If k is smaller than -1, well, I think we know what that's going to do. It's going to horizontally compress it, and it still stays reflected along the y. So let's go back. So reflects along y-axis, horizontally compressed by factor 1 over k. All right, so these ones are definitely tougher, A and K. We'll now look at D and C. Okay, if you want, you can pause the video and maybe make some guesses. If D is greater than 0. So let's go here. Let's reset this back to 1. Okay, now we'll change D. So notice D slowly moving. Okay, if you look at our x-axis, each square actually represents about 90 degrees. So as we move D to 10, the red graph is moving slowly to the right. Okay, I'm actually going to increase the value of this. Here we'll go from negative, we'll go 45 degrees. For some reason, it's doing double digits every time I hit it. Negative 45, there we go. All the way, we'll go up until 90, positive 90. And we can increment by, we'll go by 20 degrees. Okay. All right, so you can see the red graph moving by the value of D. Okay, so if we shift the blue graph 90 to the right, it would fall on the red one. Okay, it might be a little bit hard to tell that that's 90. So I'll zoom in, and you can see it moved exactly over 90. So if D is positive, it goes to the right. So we can go ahead and say that. Shifts right, 90, not 90 degrees, D units. Okay, and if we go back the other way, if we make D negative, it starts going to the left. Okay, so we can say shift left D units. Okay, lastly, our value for C, let's just reset D to 0. Okay, so if we make C greater than 0, it goes up. C less than 0, it goes down. So we can say shifts up, not D, C units. And if C is less than 0, it's just going to shift down C units. So notice from all of these, we can now actually apply many transformations to sine. We can also do it to cos as well. And we can get many other different variations of this sine graph. What's nice is we'll get the periodic behavior, which we need for modeling real life applications. And we can play around with A to get the proper amplitude. We can play around with K to get the proper period. And then we can do our phase shifts and vertical shifts as needed. Okay, that is it for this first video. This was just the investigation of sine. If you would want to, you could go back to here and you could change sine to cos, and you could then see how everything affects the cos graph. It does exactly the same way as it does for sine, so a little spoiler alert there. Let's go back to cos. Okay, then you just have to make sure you change that one too as well. Okay, be careful with those brackets. They need to be in the right spots. So there we go. Okay, so you can see all of them kind of do the same thing. Okay, go ahead and play around with this and then kind of get comfortable with all the transformations. So, like I said earlier, that's it for the first video. And the next one, we'll start our first example.